Okay, good evening and welcome back. So I'm going to recall what we have done last week. Then the first part of this lecture is not so difficult. The last part, and I'm not sure we will be able to do it today, is a bit more difficult, but okay, let's see. I remind you, we have a manifold. This is a smooth vector field. This is a set of smooth vector field. You can think about a smooth vector field as this picture. At every point, you have one vector in the tangent bundle. So on the tangent plane, you have one vector at every point. And this statement we have seen is that if you choose a point P on the manifold, there exists a flow. So what is a flow? It's a function of time and of space. And the statement is for any P, you can find a delta, which is a small time, on the neighborhood of the point P. This is this red region, such that the flow is defined on these two things with value in M. And it satisfies the following thing. At time 0, you are exactly at this point, so at any point on V. And the derivative with respect to time of this flow is a vector field. So it means precisely you have this curve, as we can see in the notes. So this is a statement about the whenever you have a vector field, you have a local flow in time. It's not clear you can extend it for all time, but precisely we say that the flow is complete if we can extend this interval of time from on R, so from -infinity to +infinity. Two more definitions. A point is regular with respect to this vector field if the vector field at this point is not 0, it is singular if the vector field at this point is 0. Okay. And it turns out that for compact manifold, all flow can be extended for all time. So it means all flow are complete. Then we have learned what is a Lie derivative either of a function, so function defined on the manifold, or of a different vector field. So you should think about a second vector field. And it's a derivative in the direction of the first vector field. So either for a function or for even the vector field y. So I gave the definition of Lie derivative of a function of a vector field. It is with respect to a given vector field. And then we switch to a different notion. So now there is no manifold for now. I take a vector space, a real vector space of finite dimension, and I define what is called its dual space as a set of all functions from V to R, which are linear. And it turns out that this is also a vector space. And in fact, the dimension of V is the same as the dimension of V star. It's dual. And I mentioned you can play with scalar product just to get an idea about what is the dual. And then we define this notion of tensor. So the notion of tensor, you have two parameters, which are integer, R and S. It's just a multilinear map. So it means you take R copies of V, S copy of V star, and you take a function which has n variables, or R variables in V, S variables in V star with value in R, and it's linear in each argument. So if you make a linear combination in any entry, you have the usual rule for linearity. And I also define the product of two tensor. I gave the definition. And we say that a tensor is symmetric if you can exchange any. Okay, for symmetric, you cannot exchange when you have elements of V, variables in V and variable in V star. So I define only symmetric here when you are only with R entries in V. It's symmetric if you can exchange any entry. It's anti-symmetric if whenever you exchange, you have a minus sign. And I introduce a group of permutation of K objects. What is a transposition? It's a very specific permutation just with an exchange of two elements. And I also introduce the signature of any permutation. It takes a value 1 or -1, depending on how many transpositions you have in one permutation. And once you have this notion, you can define these two operations, either S or A, which take a tensor of this type, send it to a new tensor of the same type. And if you apply S, you symmetrize. So you're going to get a tensor which is symmetric. Or if you apply A, you get a tensor which is antisymmetric. And there are formulas. And I mentioned some properties. You can easily show these properties just by applying mechanically these definitions. And finally, I introduce this what is called the tensor algebra. You should just think of this as a vector. You take, so the definition is that you have one element in T0, tau 0, which is, we define it as R, then one element of T1, so it's only of one variable, then an element, a multilinear, two linear maps on V, and so on. And you just think about a first component here, a zero component in this one, a first component in this one, a second component in this one. So it's like a vector. And we can define on this a product which is just an extension of the product here, because here we define this product on any tensor R on any tensor R1 and R2. You can just do this product by linearity I explained last one. We tried to do it last time with some mistakes. And it turned out it's also a unital algebra, because if you take the vector 1, 0, 0, 0, this one is just the one of the real numbers. And you apply this multiplication, you will see that 1 times any phi is just the same phi. Just look at the definition. And let me finish with this. Last week, I showed you a paper written in Japanese, which had the picture of this first course. And in fact, they mention our course. It has been translated, and it's now in the journal, which is called Japan Times. And I put a link, or in fact, I copied and pasted the paper, and now it's available on the website. You can find a link. Okay, so it's a good point, because it shows that such a course attracts the attention, because it's offered to all students. If you have any question, you can ask me at any time or by email. And I have been a little bit slow recently about reports. I will catch up tomorrow or the day after. So look, here we define this tensor algebra. We don't care if this is always symmetric. It's just a real number. There is no question of symmetry and antisymmetry. And when you have only one entry, you also cannot speak about symmetry and antisymmetry. So it makes really a difference here when you have two entries. Here we take both symmetric, antisymmetric, or things which have no special symmetry. But now I'm going to take a subset of this. So let me define, I set essentially the same thing, B, which is going to be the 1 with a 0 plus the 1 with a 1 plus lambda 2 of V plus lambda 3 of V. And you continue. Remember, these are the antisymmetric or skew adjoint tensors. You can wonder, oh, it's clearly a subset because you choose only some of them. Is it a subalgebra? What do you think? Is it a subalgebra? So is it stable when you take a product of two elements here? Why? So the answer is no, because remember, these are antisymmetric. When you multiply with the rule I gave you two antisymmetric things, you have no reason to be able to commute the entries and have something antisymmetric. So it's not, it's a subset or even a subspace. You can do addition. subspace of what is here, the tensor algebra, but not an algebra, not an algebra, because the product is not the result of a product. If you multiply two antisymmetric tensors, it's not always antisymmetric. The result of a product is not always antisymmetric. So it means it's not a good structure like this, but we have a way to correct this. We define a new product which precisely antisymmetrizes everything. So we define a new product, which is called the wedge product. We define phi product with psi. Oh, should write psi maybe. With psi. And essentially what I have to do is A of phi times psi. Because if I do this antisymmetrization, it's going to be antisymmetric. And there is a normalization factor. It's r plus s factorial divided by r factorial s factorial. If phi is in lambda r of v, psi is in lambda s of v. And you can easily observe that it's going now to be stable, because when you multiply with something and antisymmetrize, it's antisymmetric and it has all the good properties you can check. So it's an exercise, or you can do it as an exercise, that this set with it's called the wedge product. The wedge product I have just defined is an algebra. So it's stable for multiplication. It's a vector space and it's stable. And it has a name. When you put with this product, it's called either the exterior algebra or also the Grassmann algebra. So think about it. It's like a couple of entries. So it's a vector, but with a certain product. And in the product, you antisymmetrize. Are you to M or to N? Okay. Yeah. Okay. Thank you. I hope there is no mistake in the note. If there is a mistake. No, I think I put the name somewhere. Okay. So we change the product such that it's stable. A few properties. So let me state it as a lemma. Again, this is a good exercise. If you are blind, you don't want to think, you just apply the definitions. Just definition. This is your problem. No, but I mean, you don't really have to think. There is nothing you need to invent. It's just take the definitions and apply them. So it's straightforward. So if you take a phi in lambda r of v, psi in lambda s of v, r and s are always positive integer, you can wonder, what about the product in the reverse order? Is it the same or not? The answer is no, but what is the relation? It is -1 power rs phi wedge psi. Exercise, check this. Second one, I'm claiming that, in fact, it is zero. This space is a zero space if, oh, I should have mentioned, let V be of dimension n. I need to get to give a name of dimension n. I'm claiming that this is zero if R is bigger than n. Again, this is an exercise. You cannot antisymmetrize if you have more variables than the dimension of the vector space. Think about it. You can start with small number, take with n is equal to 2, and you will see. So it's a zero vector space as soon as R is bigger than 0. Now, the dimension of this it's a tensor, so it's a set of tensor. You can check it's a linear map on R copy of V, but it's antisymmetric. You can check the dimension. It is with this notation NR for R smaller or equal to n. This is a binomial coefficient. So you need to think about why, when you antisymmetrize, you get this number of. And now, Heavy-Do, there is something for you because you did it already last year. What is the dimension of the full space? You just need to sum these numbers from R is equal to 1 up to n. What is the sum of this factorial, this binomial coefficient when you sum? It is 2 power n. This is something you can check. So what does it mean? It means that when I do this, I don't need to go up to infinity. I don't have to continue. Because at a certain point, after n terms, or n plus 1 term, I have only 0. While this was not the case when I don't antisymmetrize. But now, because of this line, it means I only need to go up to lambda n of V. The last one is this one, because all the other terms are 0. I'm not going to copy an infinite number of times 0. And so this is a vector space, and its dimension is 2 power n. So we are going to play with this exterior algebra or Grassmann algebra in the future. It plays an important role. It's a set of multilinear maps on V. Just a small remark. I need to write it, but not so important. If we have two vector space, these are two vector space. And G is a linear map. So you can think about a matrix. It's a matrix from V to W. I'm going to set G star, which is from W. So I'm going to define a map from the set of tensor of degree R on W to the set of tensor of degree R on V by G star on a tensor evaluated at V1 up to VR is equal to this. The definition phi of, oh, who can tell me what to write? There is only one option. G takes a V and send it to W. So I can just write G apply to V1, G apply to V2, up to G apply to VR. And let's check This is now an element of W. This is an element of W. This is an element of W. So you can apply phi. I didn't mention, but yeah, by definition, the phi is in this space. So it's a multilinear map on R copies of W. I have R copies or R elements in W. I apply phi, it's a number. And I give this definition, this tensor, I bring it back to a tensor on V like this. That's the only definition you can put. So it means when you have a linear map between two vector space, you have automatically a linear map between tensor, but be careful of the order. It goes from the final space to the initial space. Yes. And you can check G star X or maps the tensor algebra W to the tensor algebra V and this wedge algebra W to this exterior algebra V. You just do it by, since you have it in each component, when you do the direct sum, you have it automatically. Okay. So far, so good. I don't think it was very difficult. Of course, you need to check the definition. Okay. 3.2, it's about dual basis and coordinate. It's a short section, coordinate coframe. So we consider still V a real finite dimensional vector space. You can always think about Rn when I say this, but and with basis, it always has a basis, which I'm going to denote by E1 up to En. I use capital letters and not small one because we have already seen them. And remember, V star, the set of linear functional, is a vector space of the same dimension. Now, there is a result which belongs to linear algebra. Of course, we can put a basis on V star. It's a vector space, a real vector space of the same dimension. So there are plenty of bases. So the statement is there exists a basis of V star, which I'm going just denoted for a second. I denoted by the n vectors are psi1, psi2 up to psi n. But with a special property, such that when you apply psi j on the vector ek, you get a number. But I want to get what is called Kronecker jk, which means it's 1 if j is equal to k, 0 otherwise. So what I do by this, I'm just choosing a special base of the second space. And the relation is when I apply one element of this. Remember, these are functional, so this notation is correct. Sometimes you can also see this notation, but it's a bit, yeah, I haven't really introduced it. But we can also see this notation. It's the application of this vector, these elements to Ek. So it means I can choose a special basis which has these special properties, and it's very useful. And in this basis, with this basis, I should write, with this basis, any V belonging to the initial vector space is given by, or you can write it as V equal to a sum j from 1 up to n, ej, you decompose it on this basis. And how do you get the coefficient? You apply psi j on V. It's a one-line exercise to check that. You can always decompose on a basis, but the exercise is to check that the coefficient, this is a real number, these coefficients are given by this. But it's a one-line exercise to check that indeed the coefficients are given by this. This basis with this property is called, there exists a basis satisfying this called, so the basis is called dual basis. V star is called the dual space. And when you choose this specific basis, of course, this basis depends on your choice of this one. So once you have chosen one basis of V, you have a dual basis which satisfies this. It's a kind of Gram orthogonalization process, Gram-Schmidt orthogonalization process. Yes?
Basis here is completely different from the topological basis that
yes, we are back to vector space. First year, first semester, a vector space has a basis. Of course, everything is related to everything. Okay, now this is a baby thing because we have just one vector space and a second one. But now we take a manifold. Now take M, a smooth manifold. P, a point in M. A coordinate basis or chart is P inside U. So you should remember you have your manifold, we have a point P, and there exists a U on a map phi, which send this on a part of, so this is U and this is phi. It maps this open set on an open set of Rn, and it's bijective. So this is a local coordinate system. And then remember at every P we have a tangent space. We have the manifold on a tangent space and a basis of the tangent space at P, so it's like a tangent space at this point, is given by, we introduce some name and some formula, is given by E J P. This is what I introduced for J from 1 up to M, and it's given by at the beginning, it's a bit surprising because you are expecting a vector, but remember the tangent space, if you don't have ambient space, it's given by this phi star minus 1 of d over dx j. First time you see it, it's a bit surprising, but now we are getting used to it. So because a tangent vector, it applies to a function, and this is how we do it. We in fact take the function, a function defined here, bring it here. Here I can differentiate with respect to the coordinates, and then I evaluate at this point. At the point phi p. So you can come back to exactly the meaning of this, but I explain it more than one. So we have at any P a basis given by this. So by what I just mentioned, there exists a dual space. And there exists a natural basis for this dual space, which is called the dual basis. Any question? Everything is quite natural. For every vector space, we have a dual space on the natural dual basis. Now, it turns out that every P, we have a tangent space. So we have a dual space and a dual basis. So they exist. Oh. We denote by T star P of M, the dual space of TPM. It's a m-dimensional space, so it has a dual which is also m-dimensional. And I just put the star here. Oh no, it's a dual space. So I did, I can write it like this, or I could write it like this, Tp of M star. But usually we take Tp star of M. Okay, and its dual basis is denoted by. Now this is, the first time again you see this notation. It's a bit strange. So I'm going to define a dual basis for this basis here. And how I denote it is denoted by dxj j from 1 up to m. This is a notation. I will try to say a bit more about this notation in a second. Okay. Just take it as a notation, what I call xi1 up to xin here. The dual basis of this at P, I write it dxj P, and j is from 1 up to m. And remember, these elements, these are linear maps. By definition of the dual space, it's a linear maps on Tp of M. It's a bit abstract because Tp of M is not completely easy to understand, but still it's an m-dimensional vector space. We have a dual. There is a dual basis. And do you remember the name I gave to? You remember the name I gave to this basis? Coordinate frame. I call this a coordinate frame. So this has a related name. It's going to be called coordinate coframe. Everything is quite natural. We have the tangent space, we have a basis, we have a dual space, we have a dual basis. Now, the notation, I need to spend a few minutes, it's not really an explanation, but it gives an idea. And in the notes, I also wrote it. So justification, it's not really a justification, but I try to explain something related to this notation. So we consider f a C-infinity function at P. So remember, we have defined this C-infinity of P. It's made, in fact, of equivalence class of function defined just here. And I'm going to define one thing. Take also X vector field, a smooth vector field. And we know what is this. Because by definition, a vector field evaluated at 1p, it's a tangent vector, it applies to a function. So this In fact, this is just a number. But by definition, a tangent vector applies to such a function and gives you a number, and it has some properties. So now I'm going to change my point of view. And this in mathematics, it's quite often, when you have two objects, usually you look at one object acting on the second one, but you can exchange the role. You can look at the second object acting on the first one. So we will see that it's exactly what I do here. I define something, I define df acting on xp. I give a definition. I define a new object acting on this vector by this formula. This is, we have seen it. This, we haven't seen it. Exercise, but it's a one-line exercise. With this definition, df is a linear, I call it linear functional, but linear functional on Tp of M. What is a linear functional? I will use this word. It's a linear map on Tp of M with value in R. Function with value in R, with values R. Why is it a linear functional? Take a linear combination, so take xp plus lambda yp, then you have it here, but we know precisely that it has this property xp plus lambda yp applied to f is xp applied to f plus lambda yp applied to f. So it's exactly linear maps on the tangent space. I just changed my point of view. Now, instead of writing xp of f, I define a new object applied to xp. This is something you just change your point of view, and this is something which is very convenient. So let's now play a bit with this definition. In particular, so if it is a linear functional or linear map from Tp of M with value in P, so it means, it implies that this dFP is an element of the dual. By definition, an element of the dual is precisely something which take an element of this TPM and send it to R and is linear. So by definition, it's an element of this. Okay. Now, for the coordinate frame, so in the framework I have just introduced before, what is DFP on EJP? Because remember, EJP is a vector of the tangent space. In fact, it defines a basis. So I take just one. So it's by definition EJP applied to F. And if we look back at what it is, it's a derivative of F composed with phi. I just write what we have already seen, dxj evaluated at phi of. This is something we have, it's a definition of this guy. Okay? Yes. So now, take a special in particular. I'm going to take a special f. Take f is equal to phi I. What is it? It's a game. what is this phi I? Remember, we have a manifold, we have a U, and we have phi sending it to Rm. But it means that phi has m components. There is a phi 1, phi 2, up to phi m. A vector, an element of Rm has m component. So if I just look at one component, it's indeed a function defined here with value in R. So the f can be just one component of the phi. So what we get then, what is d phi I on this EJ here with d of phi I composed with phi minus 1 divided. Who can guess what it is? Look, when you take the I component, in fact, you can remove it here and take it I component, the same. And you have the identity. Phi minus 1 phi is the identity. So you have x, take the derivative of x by xj, or component I of x derivative with respect to xj. It's Kronecker delta. You have dx I divided by dxj. By definition of what is the derivative of a function with respect to a variable, if there is not this variable in this function, then it's 0. If x is I, if I is j, you have exactly the same thing, so it's 1. So it makes delta ij, which is 1 if I is equal to j, 0 otherwise. So it means we have just defined a dual basis. So it implies that the set d phi I for d phi I use a notation d phi I p, and if I take all I from 1 up to m, is the dual basis. The dual basis of T P of M. It satisfies exactly the relation that I mentioned before. And now, usually we don't, in this case, we don't write phi I, but I have already mentioned once that instead of this phi I, we sometimes simply put xi as the coordinate of a point here. So I end up with a notation. This. So this is just a, instead of writing phi I, it just means I use a coordinate. It's just another notation. Coordinate of P in M through the chart. If you look back in the notes, I have already once mentioned that we don't always write phi I or phi. We sometimes write just x. And now you understand why I mentioned the dual basis. I use this notation dxi. And you remember here I mentioned when we have this dual basis, we can write any element as a linear combination, so on a basis. So I'm going to write exactly the same. Then, so once we realize that this is indeed a good notation for the dual basis, then any element of TP star of M can be written on the basis which is given by dxi p for I from 1 up to m. And in particular, I'm going to take one special element, dfp. Remember this dfp I started with, I told you it's an element of the dual. I can write it on the basis dxi t. And what is, should I use I or J? Yeah. And what people write is just this notation, which I don't fully like. I don't really like it because it's not really meaningful. If you think about it, it has not really any meaning. But how you should understand this, the way we have to understand it, this is d of f composed with phi, derivative with respect to xi. Now it's meaningful, evaluated at phi of p. And this is indeed f or df applied on EJP. So everything is coherent. And maybe if you have done an advanced calculus course, you have seen this. This is nothing but what is called the differential of f. We don't see it like this in calculus 2. It would be part of calculus 3. But yeah, we haven't seen it like this. Phi inverse, yes, thank you. People in economics see this kind of notation for differential without any explanation. So in some students see this notion of differential, but okay, now I have introduced everything. We have seen this is an element of TPM joint. We have a basis I mentioned, and we just, these are the coefficients. Okay, and if you delete, now if you delete P, so everything is done at a given P, but if you now look at it as a function on M, because look, we have chosen, everything is evaluated at a P, so it means I did a computation at a given P, but now I can consider it as a function on the manifold, so I forget P, so it means if we forget P, means we take for any P, we get this df is an element. What can you guess? So at every P, it was an element of this space here, dual space. I'm claiming that this is an element of, oh, but I haven't introduced it yet, so I will do it in a second. Let me already mention it, but I haven't introduced this yet. I will do it in a second. So we are going to see that it's an element of this. You can guess. It's a function defined on P, and it's a function defined on M, and at every point you have an element of this, and we are going to see that indeed it's the case. But yeah, I just anticipate a little bit. Any question? Yes. So far, we don't have higher derivative. We have derivative, we have smoothness. So in a sense, we have all derivatives somewhere. But in this expression, only the first derivative appears.
This is the basis for the vector field.
So we have a manifold, we have at every point a tangent space, and these Ej, it's no more written. The Ej are a basis on every tangent space, and now these guys are the dual basis at every point.
You don't need higher derivatives.
Not for this, not for now. Okay, now section 3.3, tensor field. And this is quite natural because, you know, except in this last part, but all the time I dealt only with one vector space. What is this vector space? V is going to be the tangent space at one point. So now I need to speak about not a tensor, but a tensor field, which is going to be a function on the manifold with value in the set of tensor. So tensor fields. Okay, so what is a tensor field? You shouldn't be surprised by this definition. So for R on S two integers, RS tensor field, so it has two, it's parameterized by two integers. Tensor field of type RS is a map phi from the manifold. Take a P goes to phi evaluated at P. So I use both evaluated at P like this or with parentheses P. Now, for every P, this is a tensor. So it's an element of tau RS of T of M. And this is clear. At every P, you have one vector space. And I'm saying that at every P, this guy is a tensor of type RS on this vector space. And if I want to write completely precisely, I started with M. I take a P. So I need to have a final space. This is included in the union over all P belonging to M of tau RS of TPS. Like the tangent bundle, it's a generalization of the tangent bundle. And it's a disjoint union because they don't overlap. So a tensor field is just a function which associates to any point a tensor on the vector space, which is given by this tangent space. All right. And in fact, you already know at least one example. What is a 0, 1 tensor field? I'm claiming that you know what is a 0, 1 tensor field, because this is just a vector, what I call just a vector field. So we have to remember what is a vector field. What is a vector field? It's a function phi from M, take a P, goes to, okay, I use X instead of phi, but it's X goes to XP belonging to TPM, right? This is a vector field. So why is it a 0, 1 tensor field?
Wedge product 1.
No, no wedge product. Ah, okay, okay, no, okay. I'll use lambda for the wedge product is of course, it's the same notation. I use this for the wedge product, but I call it lambda. I should not just lambda RS of V. So this is what you have in mind, right? Okay, so what, say it again, what you want.
Basis in lambda 1 of the vector field, therefore 0, 1.
So what is a 0, 1 tensor field? So let's check that it's the same. It's a phi from M, take a P, goes to a 0, 1 tensor. So it's a phi P, which is a tau 0, 1 of TPM. But what is a 0, 1 TPM? Remember this, it's a linear functional on the dual of this. So this, you have to think for a second. This, or maybe I should do it separately. Oh, sorry. It's not completely trivial. What is an element? Okay, I don't want to use a different notation. So what is this? It's a linear map on, if 0, 0, 1, it's on the dual space. So it's a linear map on TP star of M, right? Or linear functional with value in R. Okay. But look, here we have, I hope I don't do a mistake. Yes, it's correct. Because an element of this, an element of TPM, it's again this duality. Okay, let me tell you the truth. We have V star is equal to V. So this is a trick. So what is it? A linear map on the dual, you can identify it's equal to V itself. So this is what we have here. We have a vector field is a function which at every point is an element of this space. And here we have a linear map on the dual space. But if a linear map on the dual space is an element of V. Just think about it. It's exactly this change of point of view I mentioned before. You change your point of view, take an element here, and then an element of the dual, it's the same as taking an element of V. So once again, an element of this space, this is a V, is the same as a linear map on the dual with value in R. So it's an element of this acting on this. So you have to think about it, but a 0, 1 tensor field is nothing but a vector field. I know it's not completely easy. But it means we had already seen one special case of this tensor field. And another special case, I'm just giving a name. So a vector field is a 0, 1, and a 1, 0. So you can, probably it's easier even in the other case. 1, 0 vector field is called covector field, which is not completely surprising because a 0, 1 is a vector field. So 1, 0 is, this is just a definition, it's a covector field. So it means at every point, you have a linear map on V, because so it means you take a phi belonging to this, it's a function, you take a P, goes to phi P, and this is a linear map on V, so it's an element on TP of M star. Again, think about it. It has to be at every point, it has to be a linear map on V. The linear map on V is an element of the dual by definition of the dual. And the last example, I need to give a name. What is a 2-0 vector field? So take a P goes to phi P. What is this phi P? It's a map TPM times TPM. It has two entries with value in R, and it is bilinear. Look, because a 2-0 at every P, you have two copies of the vector space, and it's a function on these two copies with value in R. It's bilinear. So this is also called bilinear, a field of bilinear map. Field of bilinear map. And we will come back to this on V or on TPM. Okay, so let me try to summarize. We had defined tensor. A tensor, it's a multilinear map on R copy of V, S copy of the dual. Now I want to do this not for one V, but this V I replace it by the tangent space at one point. And I want to do it for all points on the manifold. So at every point of the manifold, I have a vector space. I can define a tensor. So a function from the manifold to these families of tensor defined at every point is called a vector field. And then I gave 3 examples. It's good to think about them. But yeah, there is nothing special if you, and you need to keep this in mind. The dual space of the dual space is a space itself. It helps you. Okay, is there any question? Now, I haven't imposed any smoothness. So I have just a function with value in the set of tensor. Of course, I want to have smoothness. How do I impose? What about the smoothness? How to define the smoothness of a tensor field? It's not completely easy because at every point you are on a different space. Okay? So there are 2 ways to do it because we have basis. Remember, one way is through basis. You have the manifold P and a tangent space Cp of M. So we have a tangent space and we have a basis. Whenever we have a chart, we have a basis with E1P, E2P. But we know that if we these are defined in terms of a chart. So if we move, we have other vectors. And in fact, everything is smooth. So I can use a basis of TPM. And we have also a basis. So we can use, I will write it more precisely, but use basis EP no, EJP for J between 1 and M of TPM. But this is not enough because tensor has R entries on this vector space and S entries in the dual. But we have already a basis of the dual. We use the basis dxj p, and now j from 1 to m of TP star of m. So this, I'm going to be more precise, but this is the idea. We have a basis of the tangent space. We have a basis of the dual space. And we are going to do a decomposition on this basis and ask that the coefficients are smooth. So this is one approach. And there is a second one, and they are equivalent. Oh, in fact, I don't have to write everything. Use these two bases and generate a basis of, so tau Rs of Tp of M. Look, there is R copy of TPM, and we have a basis for each of them. There is S copies of TPM star. We have a basis. So we can create a basis for this big space. It's a bit complicated, but you know, it's like if you have a basis for 2 dimension, you add 2 dimension. It's in 4 dimension. But if you have a basis here and a basis in the orthogonal space, you have a basis for this 4-dimensional space. So here it's the same. We have a basis for each copy of TPM. We have a basis for each copy of TP star of M. We have a basis for this big space. And once you have a basis, you decompose. Then decompose phi p on this basis. So you create a basis of this space, you decompose phi p on this basis, and require that the coefficients, and the coefficients depend on what? They depend on P. You do it at every point. So now you ask that these coefficients are just numbers. So, but they depend on P. So when you move on the manifold, you ask that these coefficients are smooth. So require that these coefficients are smooth as functions of. I encourage you, if you haven't done any report, this is a possible one, to think about what is the meaning of this construction. But it's quite clear. You have a basis for every point, so you can decompose on this basis. Now it depends on the point. So this coefficient has to be smooth when you go from one point to a different one. This is one way to define smoothness, as that the coefficients, and the coefficients are just real numbers. The coefficients are just real numbers, but they depend on P. So you have function on the manifold with value in R, and we know what is smoothness. And the second approach, alternatively, and they are equivalent, alternatively. Consider, so I take R vector field, or smooth vector field, R, smooth vector field. Remember, vector field is a function from the manifold to the tangent space. And consider y1 up to ys smooth covector field. And I have introduced this just before. A vector field has value in the tangent space. A covector field has values in the dual space. But it's the same. And then for phi tensor field, consider. So phi of x1 up to xr, y1 up to ys. Please tell me, what is this object? I'm claiming that this is a function defined on M with value in R. I'm claiming that this is a function on M with value in R. Why? Because when you evaluate at a P, when you evaluate this at a P, this is just a tangent vector. The same here, it's a tangent vector. It's a tangent vector, and here you have an element of the dual space. So it's a vector in the dual space up to here. So this is exactly what a tensor can have, R vectors on the tangent space, S elements on the dual, so you get a number. So this is when you evaluate at a point. So it means now, before evaluating, you have a function from M to R, and you ask and impose that this function is smooth. And we know what is a smooth function from M to R. I will not insist more on this, but it means we have two ways to check that a tensor field, a function from M to the set of tensor, is smooth, either by applying on what you can apply and asking that this function from M to R is smooth, or do it with decomposition on a basis and ask that all coefficients are smooth. Okay, I know it was not easy, but you can think about it. And if you look at any book dealing with these questions, when they do a decomposition on a basis, it's always very nasty because you have plenty of indices. There is no way to avoid this. Okay, so let me just give a name now, or notation, definition. The set of smooth RS tensor field is denoted by this curly RS on M, which is not surprising. It means it's a function on M with value in the set of tensor at every point. No, not of M, of the manifold. I didn't use it before for tensor. I have introduced lambda. No, I haven't introduced this one at all. Okay, now some special cases. And these, in fact, only one case is very interesting. Remember, tensor, they can be symmetric or antisymmetric, or not at all, or nothing. But there are some tensor which are symmetric, some tensor which are antisymmetric, and these are the interesting ones. So you can already guess, if at every point of the manifold you have a symmetric tensor, we are going to give a notation. If at every point of the manifold we have an antisymmetric tensor, we are going to give a notation. So definition, consider phi belonging to this. For symmetric or antisymmetric, I don't play with R and S because I would have variables of two types. So I only consider tau R0 of M, which is tau. I just use the notation tau R of M. So I already did something like this. When it's 0, I forget it. If phi at a point belong to so what does it mean? It means is symmetric. This is a meaning. It means is symmetric. If this is symmetric for any p, then I'm going to say that this is a symmetric tensor field. Then phi is a symmetric tensor field. And I will use denoted by phi belong to this sigma R of M. So the set of symmetric tensor field is going to be written like this. And now if phi is antisymmetric, if phi p is antisymmetric, and this is the notation I have introduced, it's in lambda R of TPM. If it is an antisymmetric vector, it's an antisymmetric tensor at every point, then for any p, I should mention, and I recall that it means antisymmetric, antisymmetric. So if it is antisymmetric, then I'm going to write, then we write phi is in this antisymmetric vector field on M. So these notations are completely natural. Before we did it for one vector space, these notations were introduced for one vector space. Now we look at functions with value in the set of symmetric tensor field or the set of function with value in the set of antisymmetric vector field. And in fact, this one will play a very important role. And there is one more which is interesting, and maybe, no, I can still have a few minutes. I can already define what is a Riemannian manifold because we have already all the ingredients. We will come back to this later, but I can already give you the definition. For R is equal to 2, consider phi belonging to sigma 2 of M. So what is this? It means that phi is a function defined on M, take a P, and it's a symmetric It's a function from TPM to TPM, its value in R, symmetric at every P. So phi P is TPM times TPM on R symmetric. And I already said that this is called also a bilinear map on TPM. I already introduced this word. Now I assume that it's symmetric, and I'm going to assume one more thing. Oh, by the way, what is a map from two vector space? You can think of it as a matrix. You can identify this as a matrix. How? Okay, it takes a vector, a second vector, and send it to R. A, V, W, one vector, a matrix. It's linear in this argument. It's linear in this argument. So an element like this, and this is what physicists do, they just identify this with a matrix. Okay. So in fact, all element of TPM, all element of map from TPM times TPM to R can be written like this, but I don't want to write it for now. But I will assume one more thing. So we consider this and assume that I'm going to assume that it is positive definite. I assume that phi P is positive. And I'm going to tell you what it is, positive definite. What does it mean? It means phi P of, I need to apply it on two vectors. I take 2 times the same, and it says that it's positive definite if this is bigger or equal to 0 with equality, so it's equal to 0. Equality. If and only if xp is 0. So this is a notion of positive definite, and you have probably already seen it in linear algebra. Matrix is positive definite if precisely when you put it on two vectors, it's bigger than 0, and 0 if and only the vector is 0. So if you have definition, if M has a bilinear vector field, this is a symmetric, bilinear and symmetric, bilinear symmetric vector field. So exactly what I have introduced, but I use the two words, either an element of this, which is well, it's already symmetric, or yeah, it means exactly this. So if it possesses a bilinear symmetric vector field, which is positive definite, then this manifold is called a Riemannian manifold. That's the definition. Then M is called Riemannian manifold. And this bilinear vector field phi, I will give a name, phi, which is positive definite, and phi is called the Riemannian metric. We will come back to this later because whenever you have a manifold with such a symmetric tensor field, which is positive definite, you can do many things. You have a way to, we don't know how to measure. So far, we don't know how to measure anything on a manifold. We don't know what is the distance. What is the distance here? We don't know what is the angle on the manifold. But precisely when you have this symmetric, and so when you have an element of this, which is positive definite, you can define this notion of angles and distance. Any question? Yes. Oh, wait. Do I do a mistake? Yeah. No, all right, I do a mistake. This sentence is not precise. I should have kept, yeah. So it has a, no, you're right, it's not correct. So, but this one is a little bit abstract. So I wanted to write something in Word, but so let me just correct it. I should have followed my note. If M, well, the correct word has a field of bilinear maps. You're right, it was not correct. Bilinear. Now it's correct with what? Yes. Now it's correct, sorry. If M has symmetric, has a field of bilinear maps of, I should write, which is, so phi, which is positive which is symmetric. I have to start with symmetric, which is symmetric and positive definite, which is symmetric and positive definite. But yeah, I wanted to write it in words because you can also replace this. You can also replace this simply by, it has a phi in sigma 2 of M, but I'm not sure it tells you more. But the precise notion is this, but we also say in this case it has a field of bilinear maps which is symmetric, and in addition we assume that it's positive definite. Okay, you are right, I was not precise. Okay, so I will stop here for today, but let's try to summarize. It's not so difficult. Don't try to look always at the details. Take a step back and have a global vision. We have a vector, we define on a vector space what is a multilinear map. And we can define it on R copy of V and S copies on the dual. And then, okay, there is a definition for multilinear map. But now you can think about this vector space is the tangent space at one point. We have plenty of tangent space on a manifold. So we want to define a tensor field. It means at every point, we associate a tensor, which is a generalization of a matrix. By mistake, or I just mentioned that, yeah, these kind of things can be identified with matrices. In fact, a tensor, physicists would say, just a collection of numbers which can be arranged like a matrix. It's not completely true, but Yeah, once we know what is a tensor field is just a collection of such things. And we have some which are symmetric, some are antisymmetric. The antisymmetric one have some special properties. We are going to continue studying them next week. But the symmetric one, and in particular the one belonging to sigma 2, are also important because if they are positive definite, they define what is called a Riemann manifold or Riemannian manifold. Okay. So next week, we will continue with this and then start integrating on a manifold, because the next step is how to define an integration on this object. Okay. I encourage you to read your notes. I encourage you to work at least on 1 or 2 exercises. Don't wait for too long. If you send me something, I will correct it now quite rapidly. Okay, thank you. Good luck if you read your notes. It's not an easy course. I'm perfectly aware that this is probably one of the most difficult ones.